Good morning, section 59. Good morning, section 59. I'll be right back. Hello, is anybody out there? Got a couple of things going here. We've got a grandson graduating, and I want to watch him walk across the stage. So we have rigged up my laptop computer to the screen of the television, and hopefully I'll be able to see. Anyway, let's see. We have one person on there. Well, I'm going to go ahead and make this video, and then you can come back and look at it. So we got as far as, let's see, what was it? Ionic bonds and covalent bonds and polar covalent bonds and nonpolar covalent bonds. So we're on page 41, and we want to look at module 2.3, chemical reactions. So you look at those learning outcomes. Don't forget, those are really valuable if you will let your mind be organized to look at something in this particular fashion. So just look over those. We're not going to get into all of them, but as you come down on page 41, you see in this first paragraph the bold print term chemical reaction. So when you think of a chemical reaction, what I want you to do is a definition for it. And you see it says anytime chemical bonds are formed or broken or rearranged, sometimes you have a swapping of elements within the reaction, and electrons might be transferring between two or more atoms. That's a chemical reaction. So let's look down at the bottom here of that first column and talk about chemical notation. That's where you get all these numbers and letters together. And so it's a series of symbols that let you know what's happening. So if you look up at the top of the page, page 41 in your textbook, and you see the reaction written out in what they call a chemical equation. And you notice you got the C and the O and the H and so forth. And so those are elements, aren't they? And you want to know that C stands for carbon and O stands for oxygen. And you see that carbon dioxide is being combined with water. And so that reaction takes place. Some bonds are broken and made, and you come up with a compound called carbonic acid. It's a weak acid. We have that acid in our bloodstream. So, excuse me, CO2 and water would be the reactants, and the carbonic acid would be the product. Now you notice you've got CO2 plus the water, and you see there's an arrow going over toward the carbonic acid. Hi, Shakira. How are you this morning? So you see that chemical reaction on page 41, Shakira. CO2 plus H2O gives you carbonic acid. So the carbon dioxide and the water, those are reactants. They are the ones that are coming together and being formed. And then you have over there to the right the product called carbonic acid. It is a weak acid. It does, and what that means is it doesn't release hydrogen ions easily. A strong acid would release those hydrogen ions and they would burn things. So that's a little simple way of remembering a strong acid from a weak acid. Now I want you to notice something. As you look at the arrows between the reactants and the product, CO2 is a reactant, water is a reactant, and the product is carbonic acid. You notice there's an arrow going back the other way. So that's what they call a reversible reaction. A reversible reaction. Now, think about the reversible reactions that occur in our body. Now, you probably have not thought about things like that, but now that you're into some physiology, you probably will begin to think about that. I just got through with a bagel and some cheese, and so and a glass of milk, and I got a cup of coffee here, a mug of coffee to enjoy a little bit, wet my throat when I'm talking with you. But I took that cheese and that bagel, and without worrying about anything about it other than the fact that it tasted good and it's got some nutrition in it, got some good protein and so forth. But we're going to take those substances which a cow made in terms of the cheese, or you can look at the bagel and you can think of the flour that is put together with some milk and some butter and some baking powder, something like that. And so we take that in and we break it down. That's a product that we're ingesting. We break it down into components. One of those components, let's say, would be glucose. And so we would take the glucose, and if we had enough in our body, we could take the glucose and turn it into a substance called glycogen, where we could store energy. Anytime you have chemical bonds, and with glucose, go back to what we haven't covered glucose yet. We're going to get to that hopefully today. It's got carbon, hydrogen, and oxygen in it. And we can take that glucose and we can turn it into glycogen in our liver and save it. And then when we need it, we can break the glycogen down into glucose. The glucose gets broken into various components so that we can produce an energy molecule called ATP, which we'll talk about later. So we've got all these reactions going on inside of our body, and you and I don't think anything about it. Shakira, you're just paying attention to me, and I'm paying attention to you. And so we're occupied with getting educated and understanding things so that we can get into a profession where we can do a good job for people. So reactions many times can go forward and they can go backward. Forward reaction, reverse reaction. Now, if you come down in the second column on page 41, you see energy. And energy is this something you sort of can't get a hold of. They have defined it, as you see in the second sentence, the capacity to do work. Now, you know, and I know that we have to have energy to drive our cars. We have to have energy to turn on the lights, to be on a piece of technology they call YouTube. So energy is the capability to do work. So things can get into motion. And you come on down a little further and it says it drives our digestion and our respiration. We are using energy. I'm using it as I'm talking. You may be taking notes. You may be thinking about these things, and you're using energy. Energy is in the bonds of chemical reactions. And so when we've got a carbon, hydrogen, oxygen all combined making a glucose, we have energy in that molecule. And because we can break that molecule down and break the bonds, then we can release energy that will enable me to move the muscles of my mouth, make neurotransmitters in my brain and my hands so that I can talk and move. We've got to have some energy. So let's look over on page, let's see, what did I do with that? There it is. Let's look on page 42. Page 42 in your textbook, or if you're in that e-text, you're looking for a title that says, you're in chapter 42 in that module, module 2.3, and you look for forms of energy. We're not going to get into this very deeply, but you just want to know there are three kinds of energy. There's chemical energy, and obviously that would deal with glucose. Oh, let's see here. What do we got? Hang on one second there, Shakira. Okay, let's see. Where were we? Thanks for your patience, Shakira. Okay, let's see here. Okay, Brandy and Brittany. Kind of challenging to do everything. I don't know. I only know one person who can do everything at the same time. And we need to know him, don't we? Okay, so we were talking about the three kinds of energy. Chemical energy, we're on the first column on page 42. And you see in bold print chemical energy, and you come down to the next paragraph, electrical energy and mechanical energy. So you just want to know those three types of energy. They all show up in our bodies in various ways. And they'll give you some examples, but just know those three types. Now, in the next column, there's a couple of terms. And you see endergonic reaction and exergonic reaction. Now, what I want you to take away from this, these two terms, ender makes you think of endo, inside, exer makes you think of exo, outside. Endergonic reactions require energy to occur, Exergonic reactions release energy. Come away with that sort of thinking. You'd think this was the firehouse, wouldn't you? Okay. So much for endergonic and exergonic. Endergonic requires energy input, and an exergonic gives off more energy. So come down to where you see homeostasis and types of chemical reactions. Basically have 2 or 3 types of chemical reactions. And so you look down at the bottom and you see catabolic reactions. And notice in the second line, it's called a decomposition reaction. Large substances are broken down into smaller ones. That's what I'm doing with the cheese. That's what I'm doing with the bagel. It's a catabolic reaction. We got to break things down. And I turn what the cheese is, which came from the cow, and the cow made the cheese. The cow made the milk, and the man made the cheese. But I turn in what I eat. I turn it into smaller pieces. That's catabolism. That's decomposition. And then you come over into 43 and you look down that column and you see there's a heading called anabolic reactions. Anabolic reactions is where you take those products that I broke down and I rearrange them into me. So I make new skins. I only have one skin, so I make new skin. I make proteins for my muscles. I make energy to be used for my thinking. Okay. So I break all those things down and then I turn them into me to produce something, to build something, as opposed to break it down. You come down and you see the word which you some of the substances that I ate this morning, and I would turn them into my proteins in the mucus of my mouth. I would turn them into fingernails. You know, your fingernails grow, so do your toenails. Well, they've got, in most cases, they got protein like keratin in them. So I take what was flour in a bagel and I break it down and reassemble it into proteins that make up my fingernails. And you could go on and on and on in what you do. But what you want to take away is a breakdown reaction is catabolism, a building chemical reaction, producing a product is called an anabolic reaction, or sometimes called anabolism, or synthesis. Synthesis is another word for producing something, putting things together. Now, I want you to look above that in that little section under exchange reactions. You see what an exchange reaction is. One or more atoms from reactants are exchanged. So you see hydrochloric acid, sodium chloride get put together. It goes one way. So the OH comes off the sodium and hooks to the other H on the hydrochloric acid, and you end up with water, and then the sodium and the chloride combine, and you have salt. That's an exchange reaction. You've simply swapped elements in the reactants and produced different products. Now you notice it says a special kind of exchange reaction is the oxidation reduction reaction, sometimes called a redox reaction. And you see it says during an oxidation reaction, electrons are exchanged instead of atoms being exchanged. The reactants lose electrons. The reactant that loses electrons is oxidized, and the reactant that gains electrons is said to be reduced. Okay? That's all you got to know about that type of reaction. Now let's come down to reaction rates and enzymes. We're not going to talk a whole lot about that, but I want you to look over on page 44. And there are several factors that can speed up a reaction. We're not going to get into all of that. That gets into a lot of chemistry, which I don't think you really need at this point. But come down in that first column and you see it says the presence or absence of a catalyst. A catalyst is a substance that speeds up a reaction. It increases the reaction rate. Now look at the next bold print term. An enzyme is in the category of a catalyst. An enzyme is a protein that usually does one thing. That's one of the interesting things about our proteins. They're very specific in their function. So if I've got an enzyme that is a muscle enzyme that causes a bond between actin and myosin or whatever, that's not necessarily true, but that enzyme is not going to break down the bagel that I had this morning. These enzymes are very specific. I see we got another person on the system. So if you would, put your name in there. I appreciate that. Just type your name in there and say, I'm here. That'll give me a record. So you want to know that a catalyst will speed up a chemical reaction. We're on page 44. Now, that's all we're going to say about that. You come over to page 45, and you're looking at a section called, on second column, 2.4. That's module 2.4. And you see inorganic compounds, water, acids, bases, and salts. So, again, look at those learning outcomes. What do you want to know about inorganic compounds? And these categories here, water, acids, bases, and salts, they're all considered inorganic compounds. If you look down at the very bottom, got a little paragraph there. Now, we're dealing a little bit with biochemistry, the chemistry of life. That's what we have living in us, don't we? And you see they group the compounds. You look at that second line, they group into one of two types of compounds, inorganic or organic compounds. Inorganic compounds do not contain carbon bonded to hydrogen, whereas organic compounds generally have that. So you look over on page 46. So if somebody asks you about inorganic compounds, you say, well, those are substances that don't have carbon and hydrogen bonded to each other. And then, of course, the opposite is the organic compound. So we deal with inorganic and organic compounds every day. One of the inorganic compounds, inorganic, it's got hydrogen, but it doesn't have carbon. You see is water on page 46. Water is it's not even very, it's vital to our existence. I think I've mentioned that we are about 80% water. So if you're a 100-pound person, 80% of your body is water. If we dehydrated the body, it would be about 20 pounds, give or take a few. Water is an amazing substance. And so you want to know these properties that are mentioned in the first column on page 46. We typically think of water as just keeping us hydrated, keeping us from being dry in the mouth, or maybe having dried up mucous membranes or something like that. But you see these properties, these characteristics of water. Absorbs heat without changing significantly in temperature itself. So that's why it's slow to warm the body up, slow to lose heat also. That's a good characteristic. So we don't have a huge swing in just a matter of a few minutes. It takes time, which gives us the opportunity sometimes to remedy a situation where a person's too high or too low or something like that. Come down to the next one. Water carries heat with it when it changes from a liquid to a gas. They call that sublimation. S-U-B-L-I-M, sublimation, N-A-T-I-O-N, nation. Now, I think most people have heard of this, but they might not give it too much thought. But here in South Carolina, that's a big deal. We sweat. I am sweating right now. Not profusely. It's not rolling off my forehead. It's not getting in my eyes. I'm not wet in my t-shirt or anything like that. But we are perspiring. Now, if I go outside, I'm gonna sweat, perspire more so. The problem with going outside in South Carolina in the summer is that the humidity, the amount of water in the air, is higher. We have days where it's 85% humidity, and you walk outside and you can just feel it sort of oppress your body. And when you sweat, which you do, it does not evaporate. You see, it says water carries heat with it when it changes from a liquid to a gas. Water can become water vapor. But if there's a lot of water vapor in the atmosphere, then this water on our skin does not evaporate. It's the evaporation of the water to a gas, water vapor, that cools our body. That's why in Arizona, you can go outside on a 110-degree day and you don't feel the sweat. You don't feel the heat because your water that's coming out of your pores evaporates and it cools the body. That's amazing, isn't it? But you come to South Carolina and the humidity is almost oppressive. You hate to go outside. That's why in South Carolina, one thing you're going to have in your car, if you can afford it, and one thing you're going to have in your house is an air conditioner. An air conditioner pulls the water out of the air in your car, in your home, so that the normal perspiration can evaporate and take heat with it. And we're comfortable. And we don't end up being wet. Okay? Look at the third one. Water cushions the body. We're not just skin and bones. We've got some water in there. And so the water is in our tissues and it acts like a cushion. It's a liquid pad that surrounds our tissues and helps to protect underlying structures. And part of that cushioning effect is due to the hydrogen bonds. You remember how the hydrogen bonds were formed between the negative side of an oxygen and connects to the positive side of the hydrogen. And so that tends to make a little net for us that protects us. And then you see at the top of the next column, water acts as a lubricant. All of you have had dry mouth from at one time in your life, and keep these eyes moisturized, and it starts hurting. If you got water in your joints, you have water in your esophagus, so that when you swallow your food, it slides down. The mucus that we talk about, it's got a little protein in it, makes it slippery, but it's still like 70–80% water. So water is really valuable to us. Now, you notice it says water is a solvent. And a solvent, of course, is a substance in which you dissolve a solute. So water is a solvent. There are substances that will dissolve in the water. There are substances that will not dissolve in the water. As you look at the picture, figure 211, and you see the 3 beakers of water, and you see a little expanded viewpoint there, you see them pointing to the water molecule. Remember, it's polar. And they put sodium and chloride ions. If you put salt in water, the sodium and the chloride break apart, and the sodium will be drawn to the negative side of the oxygen, and the chloride will be drawn closely to the hydrogen ions because it's negative. The hydrogen ions are positive. So that the fact that you've got these hydrogen bonds creates some sort of an electrical type of attraction. Now notice underneath the beaker it says ionic compounds are hydrophilic. The hydro, means water. Philic means to love. So if we say something is hydrophilic, we mean basically, we're not talking about love like out of our heart or something like that, but it likes to bond to the positive or the negative aspects of the water molecule. So something that's hydrophilic will dissolve in water. So ionic compounds are hydrophilic. Remember, they donate an electron to another molecule, producing ions. One's negative, one's positive, and so that tends to hold them together. So they donate. But come down to the middle, polar covalent compounds, those are hydrophilic also. Some of the substances that you and I eat are hydrophilic. They like water because they're slightly polar. Remember, that means the charges, I should say this, the electrons that are shared are not shared equally. So we get a little bit of polarity, and therefore they tend to dissolve in water, like sugar. You put sugar in water and you stir it up, and it disappears, doesn't it? It goes into solution. But come down to the bottom where you see nonpolar covalent compounds, they're hydrophobic. Phobic means to have a fear of. And of course, hydro tells you it's about water. Hydrophobic. Notice to the right of the little circle with the methane molecules in there, you see it says they lack positive and negative charges, and so they have nothing to interact with the water. Shakira, what kind of salad dressing do you like? Do you have to shake it up before you put it on your salad? Yes, you do. Next time you're going to have yourself a good salad and put some Italian dressing on it, look at it before you pour it, and you're going to see separate liquids. One liquid's going to be water, the other's going to be oil. That's because the oil is nonpolar and the water that's in there is polar. Nonpolar substances, like oils, do not like water, so they don't dissolve in it. So they're called hydrophobic. Okay. So over on in your handout that I sent you, you see over on page 47, you see quick check. So make sure you are reading those, trying to answer them. Another example of the polar and nonpolar substances not mixing. We've all cooked bacon before. I know when we make chili, one of us will ground not ground, but we will brown the ground meat. And so we brown it, and then we pour off the liquid that comes out. Now, we usually, when we make chili, we open all the cans and, get the tomatoes out and so forth. And we'll use one of those cans to pour in the liquid coming off the ground beef. So when that happens and you let it sit for a while, you've got this fat layer on top, and underneath is water. The fat is nonpolar. The water is polar. They do not dissolve. They do not mix, just like your Italian dressing. So, having said that, let's look at acids and bases. And you see this acids, the study of acids and bases is really about the study of the hydrogen ion. It also deals with the hydroxide ion as you come down to the bottom. But as you see, when you take hydrochloric acid, a little picture to the left, hydrochloric acid, you put it in the water and it breaks. So it ionizes into a hydrogen ion and a chloride ion. Therefore, it's going to dissolve in water. You'll see it separate like that, and it'll hook to either the OH or the oxygen of the water molecule. So an acid is basically dealing with releasing hydrogen ions. Look over on page 48. And if you had to define an acid, generally speaking, then you would take that first term up there. An acid is a hydrogen ion donor. It is a substance that donates hydrogen ions. Now, the more easily it gives up its hydrogen ion, the stronger that acid is. There are some acids that you can put on your skin, it'll just eat right through your skin. It'll do what they call burn you. You'll get acid burns. So an acid is a hydrogen donor. And you come down to, you can see carbonic acid. In the 2 paragraph says examples of acid found in the human body. Hydrochloric acid in your stomach. Most of you have probably vomited at one time. And when you do that, sometimes the material from your stomach comes through your nasal passage. It burns, doesn't it? That's because it's hydrochloric acid. Now, it's been mixed with some food probably, and you're throwing that food back up, and that helps to protect your mucous membranes. But hydrochloric acid, strong hydrochloric acid, can burn you really well. It's very strong in your stomach. That's why you want to put things in your stomach, because the acid that's produced can actually dissolve part of your stomach. So sometimes going without food for a period of time is not the best thing. Come down to where the next dot is, the next bullet. You see it says a base is a hydrogen ion acceptor. And so It's also called an alkali. So the hydroxyl ions are the ones, hydroxide ions are the ones that are in greater concentration as opposed to the H concentration. Now you're looking on page 48 and you see they talk about the pH scale. And you see the two bars, figure 213. Look right in the middle of those two bars, and right in the middle you see this number 7. 7 is considered neutral. In other words, there's enough hydroxide ions, that's the OH, and the hydrogen. They are, we'll say equal. Might not be perfectly equal, but they're equal. We'll just call them equal. And so we say that pH is neutral. Obviously, there's some people who are neutral in terms of politics or whatever. And so a solution can be neutral. Hydroxide ions equal the number of hydrogen ions. That's what we typically think of as water. Now, as you look at the left-hand column, you see the hydrogen ion concentration. As you see the little dots in there, they become fewer and fewer and fewer. We're going into a basic, an alkaline pH. In other words, there are going to be very few hydrogen ions in that situation. And you see what they've got is ammonia up there as an example of a base. It's going to accept a hydrogen ion. And then you come on down, you see baking soda. That's sort of basic, isn't it? It's above 7. Then you come to 7, which is pure water. And now you come down. Now, the cup of coffee I had this morning has a pH of about 5, which is slightly acid. And then you come on down, and you said you like Italian dressing. So you've got vinegar and water in there. Vinegar is an acid somewhere around the pH of 3. Lemon juice usually makes us pucker up. Pretty good acid. Kind of, but I like the flavor of lemon. I like lemon in tea. But just to suck on a lemon, whew, you can see the acid is pretty strong, 2.5. pH is 2.5. You come down to stomach acid, anywhere below 2. Very acidic. A lot of hydrogen ions. So the lower the pH, the greater the number of hydrogen ions. Now they're going to, they talk in the down below. We've already covered that to some degree about a pH greater than 7 or less than 7. Now come down to the bottom paragraph, the next to the last one, and you see it says the pH of the human body hovers just above the neutral part. Now that's really talking about the bloodstream. The pH of the bloodstream should be between 7.35 and 7.45. You want to remember that. So if we have a problem sometimes, it's usually because the pH goes below 7.35. So if you have a 7.1, you're in what they call acidosis. Spell the word acid and add OSIS to it. And so that means OSIS is a condition. Acid is a condition of too much acid. Okay? So you want to remember that, because just as acid in your stomach can burn your mouth and burn your nasal passage, it's destroying proteins, is what it's doing. Now, we have a lot of proteins in our bloodstream. You're not going to go learn all of them, but we have proteins that play a role in our bloodstream. If our pH goes down to 7.1 or 7, our proteins start to unravel. It's like taking this shirt, and it's got a pattern to it. You can see it. But if we put it in acid, those threads will come apart. Well, the same thing happens with the protein. And when the protein changes its shape, it doesn't work. And that means we're headed for the grave. Our body is going to break down if the pH gets too low. We'll talk about all that a little bit later in 211. Now, when you come to the last paragraph, you see in the last paragraph, something important to note about the pH scale is that we're dealing with a base 10 logarithm. Don't worry about logarithms. Not going to get into that. What I want you to recognize, if you will come down from where you see logarithm down 1, 2 lines and look over to the right. So when the pH decreases from 7 to 6, the hydrogen ion concentration increases 10 times. And you got 10 more times the hydrogen ions at 6 than you do at 7. If you go to 5, you have another 0 added onto it. Now you have 100 times the normal hydrogen ions. You go to 4, you add another 0. It's 1,000 times more concentrated with hydrogen ions. You get the picture? All you got to do is add a 0. So the pH, the number of hydrogen ions is going to change from 7 to 6 in that it is going to have 10 times more hydrogen ions than it did at 7. Just remember that. Don't worry about logarithms. Okay? Don't worry about that. You can read through that several times. Just keep remembering all you're doing every time you go from 7 to 6 or 6 to 5 or 5 to 4, you're adding another 0. So you can see you real low pH, you can get up to 10,000, 100,000, more than you would have normally at the pH of 7. Okay, serious situation. Now, let's go to page 49. Let's talk about buffers for just a minute. Buffers are good. We have several of them in our body. You see what it says? The reason that the pH range in our body and cell is so narrow is that the function of many important molecules in the body, such as enzymes and other proteins, can be disrupted by even slight changes in hydrogen ion concentration. We don't want that variation in hydrogen ion in concentration. Let's see what we got. Okay. So come down to the second paragraph under buffers, and you see it says it's a chemical system that resists changes in the pH. We've got 4 buffers in our tissues. Now, we're not going to get into all of those because you will get a brain full of them when you get into 211. But you see what the point is, the purpose of the buffer. What is a buffer? You say it's a chemical system that prevents large changes in the hydrogen ion concentration. That's your definition for a buffer. Now I'm going to give you the name of one. You will get a dose of that stuff in the second semester. Look at the last sentence. And you see it says the carbonic acid bicarbonate buffer system. Shakira, you ever taken Tums or Rolaids or a spoonful of baking soda? You ever done that? Well, you were buffering your stomach. You might have had some acid indigestion. You put a couple of Rolaids in there, Tums, or they used to have Gelucils when I was a kid, and that was a tablet that was it was a substance which tends to take up the hydrogen ions. If it hooks up to the hydrogen ions, then the concentration of the hydrogen ion becomes lower, and the pH rises back to what it should be, whatever that level is at that point. It sounds a little bit opposite. You're saying a lot of things. You're going to drop the hydrogen ion concentration, but you're going to raise the pH. That's right. pH is 7, you have an equal number of hydroxide ions and hydrogen ions. But if you go to 6, you get more hydrogen ions, which lowers the pH. Just got to remember it like that. I know it sounds oppositional, but that's the way it is. Okay? So one buffer system that we have is called the carbonic acid. That's a weak acid as opposed to a strong acid. And it has a bicarbonate in it, and that's what they call it. Carbonic acid bicarbonate buffer system. Are you talking, Noah?
Yeah, Drew's going to be up there soon.
Okay. Okay, we've been going here now for about an hour. Let's take about 5 minutes, 5 or 10 minutes, okay? And we'll come back. I'll be right back with you. We'll get into salts and electrolytes, okay? I'll be back in just a moment. Okay, you back, Shakira? Are you back there, Shakira? Okay, great. So let's go down to salts and electrolytes. And salts, you come down into the paragraph there, and it says it refers to any metal. Remember how we divided the periodic table into on this right-hand side? It's my left over here, but you're looking at me, so it's over here on the right-hand side. And so you have metals on that side, remember the little red staircase? And then you have non-metals on that far side to the right, and then over on the left, you've got the metals. And so you see it says the salt is a combination of a metal cation, positive ion, and a non-metal anion. That's why you say sodium and chloride. Sodium chloride is salt. It is a salt. We often talk about that. But there are a number of different salts, like magnesium chloride could also be called a salt. When you put them in a solution, when you drop them in water, they come apart. And you have charged particles all through the solution. And so those particles now are called electrolytes. They will conduct electricity. That's important. We have electricity occurring in our body, and we can measure that. That's why people can get what they call an EEG, an electroencephalograph. That's or gram rather, I should say, and that's a measure of the electricity going on inside your brain. Come to the very bottom of the paragraph, and you will see salts play a wide range of vital roles in the body. Calcium phosphate. Calcium is your cation, positively charged. A phosphate group, PO4, is negative, and that's always on that left-hand side or the right-hand side of the periodic table. Potassium and the oxygen. Those salts are important in our bones, in our teeth. So you come over to page 50. Now, in that handout, I told you to look at those quick checks. What is a salt? Just keep going over it and over it. That's the only way to get it in there. It's just like playing a piano piece. You got to play it over and over and over so you have it down pat. And then you just make yourself smile when I grade that. And I turn back to you, oh, you made a 97, 92, something like that. You do have a brain, and those connections are being built well. So anyway, don't forget to do those quick checks. All right, now, so we're through with 2.4. Those were the inorganic compounds. Now we're going to look at the organic compounds. Gets a bit more complicated with them, and there are a number of classes of them. So on page 50, you come down to module 2.5, and you see we got organic compounds. What does an organic compound consist of? Carbon, hydrogen, and then you have oxygen in there also. So under learning outcomes, again, look at those before you get into reading this. I'm giving you some information now, but look at them and get your mind set to be looking for these sort of things. So down there at the bottom it says certain organic compounds called hydrocarbons only contain hydrogen and carbon. And you see at the last sentence, they can be in chains and they can be in rings. So you look up at the top and you see this chain of carbon atoms, and they have hydrogen atoms around them. Those on the end have 3 hydrogens. Those in the middle have 2 hydrogens. And you can think of perhaps some people who heat with propane or butane. Propane is a fuel that we can burn. We get gasoline from them. We get natural gas and so forth. Those are hydrocarbons. And then here you see another hydrocarbon that can actually be in a ring. Now you see that ring has 6 sides to it. They would call that a hexane. Hex meaning 6. And then you can hook different, you see they got hydrogen on there too, but you can change some of those hydrogens to other substances and you get another product that we'll talk about a little bit later. So, you know about organic compounds. This is what we're looking at. They got a carbon and hydrogen, quite a few of those. And you come down to right underneath that little ring and you see the carbon hydrogen backbone forms the basis of all our organic compounds with the additional groups of atoms called functional groups. You'll see those in just a few minutes. The organic compounds covered in this chapter: carbohydrates, lipids, proteins, and nucleic acids. So we're going to see how far we can go in about 30 minutes, and then we'll take a weekend break. I hope you guys are doing your assigned duties. Does everybody know how to get to those assignments? Get into Mastering A&P for students, then go to Mastering A&P Home, and then you see this word assignments. I think it is, let's see if I got it written down here, upcoming assignments. Click on that, look at the assignments and the date they're due. Now you don't have to wait to get that thing in, but it does take time to get these assignments in. So get them in because you can get yourself a grade that's going to be good for your lecture exam and your lab, your lecture average and your lab average. So let's start with monomers and polymers. Mono means one, right? Even when you have an infection called mononucleosis, that's a cell that's got one piece of nuclear material. Some of them have several, and that cell grows out of control. So that's why they call it mononucleo, one nucleus, osis, condition of. If you've ever had mononucleosis, not fun to have. Never have had it. But people say, oh, I wish you could eat for me and go to bed for me and take a shower for me because they're so tired. All your energy is going to fighting that virus that causes the problem. Second column, monomers and polymers. Monomers are the excuse me, single, as you see, subunits, kind of like our alphabet, okay, to some respect. Got letters, all these different letters. Those are the monomers. You put them in the right sequence and you get some words have 10 or 15 letters in them, and those are the polymers. So we have big words, we have little words, and then we can take them all apart and have little A, B, C, D, E, F, G, okay? So that's what we're talking about. Monomers, single units, polymers, hooking those single units in some fashion. Come to the second paragraph. You see polymers are built by anabolic reaction. Remember, what is anabolism? You're going to see these things on the test. Anabolism is the situation in which you build a molecule. You build a substance as opposed to break it down. And then you see it says another way to put anabolism is dehydration synthesis. Means you take out some water from two molecules. You take out a hydrogen from one molecule and a hydroxide from another. I know this all the time. When we make proteins, we hook amino acids together and we pull out a hydrogen and a hydroxide and hook the amino acids together. That's dehydration synthesis, making a larger substance. On the other hand, as you come in this paragraph, Down from where you see dehydration, synthesis, come down 1, 2, 3, and you see hydrolysis. Hydro is the root word for water, could be also for hydrogen. And then lysis means to split. So using water and one of those enzymes that we talked about a few minutes ago, we lyse a substance and we break it into monomers. So we use catabolic reactions to build polymers. We use water and enzymes to break polymers down into monomers. The polymers are too big for us to absorb into our bloodstream. We have to break them into monomers. So those are terms that you want to know about. So we come down to carbohydrates. And there's a great question in Quick Check. Start thinking about that. I'm going to be starting to build up a test for next week. Test is next Thursday. So we'll do that next Thursday, okay? Okay, talks about the chemical bonds in these carbohydrates. What type of chemical bonds? This is a flashback. And of course, we're talking about covalent bonds, aren't we? We're not talking about ionic bonds. We're talking about covalent bonds. And they tend to be, in this case, polar, because we're going to throw some oxygens in there too. Now it says number 2 up there at the top under flashback are compounds with these types of bonds, hydrophilic or hydrophobic. Well, I'll let you wrestle with that. Okay, and why? Okay, let's look at the carbohydrates. You talk about carbohydrates, we're talking about carbon, hydrogen, and oxygen. It's got some oxygen in it. You have hydrated a carbon molecule. And so you come up with this name called carbohydrates. Whew. Got to have a little more breakfast, I think, next time. Notice in that first paragraph, in the last sentence, an example of a functional group, the hydroxyl group being an example of a functional group. The molecules on the whole are polar. They're polar, water's polar, so carbohydrates like water, therefore they're hydrophilic. So you come down from that paragraph, you come down to skip that middle paragraph. We know that we use carbohydrates for fuel, for our energy. We eat sugar, we eat starches and things like that, and bread and biscuits and so forth. Pasta, some of you like pasta. And so you come down to the next paragraph, it talks about the monomer of a carbohydrate is a simple sugar, more formally called a monosaccharide. Okay, monosaccharide. Look up at the top of the page. Figure 214. Carbohydrates. Structure of monosaccharides. Now notice the two on the left. You see those two are built like a pentagon. You know the Pentagon up in Washington that those Islamic extremists, radicals, wanted to destroy. They want to attack that building by driving a plane into the middle of it. But you see they have 5 sides to them, right? Pentagon. Now, count your carbons in there. Starting with at the left, you see 1, 2, 3, 4, 5 carbons. Now, 4 carbons make the pentagon ring. So we call them pentoses. You got 5 carbons, but you only have 4 carbons actually helping to make the ring, and you got an oxygen there in the middle. Now look at the title of the 2 pentoses, deoxyribose and ribose. And you see the chemical formula for them, C5H10O4. As you look at the carbohydrates, many times you're going to see the carbon atoms are duplicated in the hydrogen. So if there's 5 carbons, there's 10 hydrogens. And then you usually have one less carbon, or one less oxygen in there. So that's a formula, chemical formula. Deoxyribose is associated with DNA. Ribose has the same, basically the same formula. It's got one extra oxygen, doesn't it? That makes a lot of difference. Those are functional groups. So, excuse me, you can see the difference between the two. If you count the carbons, starting on the left-hand side of deoxyribose, look at that carbon sticking off up from that corner. You see 1 carbon, 2 carbon, 3 carbon, 4 carbon. Everybody sees that, I hope. And you see hanging off that 4th carbon, you have a hydrogen, 2 hydrogen molecules. Go to the right, count 4 again, 1, 2, 3, 4, and you see there's an oxygen and a hydrogen there, a hydroxide ion. Makes the difference. Got an extra oxygen in there. You can count those off. That extra oxygen's on that 4th carbon, depending on which way you come and count. But deoxyribose and ribose are in the nucleus, and they play roles in controlling all the activities that go on inside our body. The ribose and the deoxyribose are involved in what we call protein synthesis. 5 carbon sugars, okay? Those are called monosaccharides. The same thing is true in the next 3 that you see to the right. And you see below these, you see these are called hexoses because they have 6 carbons in. Even though the middle one, fructose, or some people call it fructose, you still have 6 carbons. It's a pentagon arrangement. Count your carbons. They're the gray ones. 1, 2, 3 on one side, 1, 2, 3 on the other. That makes a lot of difference. 1 carbon, a few more hydrogens, another oxygen or whatever, makes a lot of difference. Those 3, glucose, which you've heard of, and you may have had some family members. Maybe you've even had an IV in your arm and they put in D5W. D stands for dextrose, which is another word for glucose. D5W. Dextrose, 5% in water. That's something that the body can use as energy, but it also hydrates a person. So we have glucose. We usually get that from sugar cane. You can get it from beets too. Come to the right, you see fructose or fructose. Think of fruit. Okay. Honey's got fructose in it. And then you look to the right, the galactose, that comes from milk. And you guys like yogurt? Do you like cream in your coffee? Do you like milk itself? You like ice cream? Okay, it's got galactose in it. There are a large number of people who can't break down lactose, which is a combination of galactose and another sugar, but it comes from milk. But notice the formulas. C6H12O6 for glucose, C6H12O6 for fructose, C6H12O6 for galactose. You think, what? They all have the same formula? That's right, they do. But their atoms are arranged differently. Same number of carbons, same number of hydrogens, same number of oxygens, but they are arranged differently. So I want you to do this, just so since we're right in that area, come down in that column, the second column, And you see glucose in bold print. You see isomers. Isomers. They all have the same chemical formula, but their carbons are arranged differently. They all have the same oxygen, same hydrogen, but they're arranged differently, and that's an isomer. Molecules, so you see it says the arrangement of the atoms is different in all three molecules, but they have the same number of carbons, same number of hydrogens, and same number of oxygens. So those are isomers. How are they different? Can you imagine me asking this question? How are they different from isotopes? Kind of a similar word, isn't it? At least with iso. Iso typically means equal. And they have the same equal number of oxygens, carbons, and hydrogens. Okay. So all of those that you see up there, the pentoses and the hexoses, they are monosaccharides. And we can attach them. I want you to look down at the bottom. We can attach these sugars together. Look at the very bottom, figure 215, and you see glucose on the bottom at left, and then you see fructose. Both are monosaccharides. Follow the top arrow where you see the term dehydration synthesis, and an enzyme would help this take place. A catalyst would help it take place. You take water out, and now you've made a bond between them. And you see it's left an oxygen, but you've taken out two hydrogens here and an oxygen off there. Okay? So now you have the sugar sucrose, which is a disaccharide. That's what you and I put in cakes and cookies. Some of you like it in your coffee. Some like it in tea. Usually comes from sugar cane, can come from lost my word. Sugar cane and something else. I can't think of what it is right now. But beets, that's what it is. Now notice when you and I take in the sucrose, look what happens to it. We break it down with water into these two monosaccharides because we can absorb the monosaccharides. We cannot absorb the disaccharides. They're too big. Okay? So let's look over now on page 52. There are a number of people who cannot break down lactose in milk, which is a combination of glucose and galactose. They don't have an enzyme for that. If you can take milk in and break it down into that, then you're in the minority. But it's nice that you're in the minority because you can break down that milk and get the energy out of it. Now, let's look on page 52, come down to polysaccharides. Poly means many. So when you think of a polysaccharide, we're going to think of just a couple of them. You're taking all these sugars, the various sugars, and you put them in a link, one after another, and you get poly, many. And notice what it says. They are the largest and least soluble. They work much better when you break them down into disaccharides or monosaccharides. That's when they can easily be dissolved in water. So, but the polysaccharides are very difficult to get them to dissolve. Now, you come to the second paragraph and you look in the third line of that second paragraph under polysaccharides, you see it says because of their structure. And you come to the third line, it says plants store their glucose in a form called starch. Now there is when you and I have a biscuit or have a sandwich, we're eating starch. Some of us think of starch when you put it on a shirt, right? Or some sort of article of clothing to make it a little stiffer. But we eat plant starch. I want you to write this down. Amylose, Amylose, amylose. Ose tells you it's a sugar, and it's a large carbohydrate. It's a polysaccharide. But when you and I bite into a biscuit and we start chewing that up and eating that, we have an enzyme called amylase. Change amylose, Amylose, and take the O out and put an A in it. And now we have a protein that is an enzyme that breaks down the starch for us. It breaks it into, we're not going to get into all that it breaks, but if you're interested, you can look it up. It's called maltose. And then we break the maltose down, and then we can absorb the breakdown products of glucose, fructose, and so forth. So starch, or amylose, is a polysaccharide. When you and I eat the muscle of an animal, hamburger, chicken breast, pork loin. Okay, somebody just said something to me. We're gonna break that glycogen down into glucose molecules, which we can absorb. Excuse me, just a second. Thank you, Shakira. My grandson just graduated. They had to get a picture of us. Okay, let's see. We were on polysaccharides. We talked about glycogens. And all right, in the muscles and in the liver of an animal. Some of us like liver hash when you go to a barbecue place. Thank you. Appreciate it, Shakira. Busy morning. Makes me glad I'm not the president of the United States. There is more downtime here. Okay, notice down at the very bottom, if you look at the little diamonds, we would say the little green diamonds, see those are glucose molecules, and you see how they're hooked together in branching chains. That's the polysaccharide. A lot of glucose is hooked end to end. So notice in the last paragraph, it talks about glycoproteins and glycolipids. Now, while I mentioned that at this point, we're eventually going to get to the cell and talk about the membrane, and glycoproteins and glycolipids are part of our cell membrane. We need lipids. We need glucose in the right amount. If we don't have it in the right amount, we're either skinny, too heavy, or whatever, or some other problems can show up. So I think that takes care of the carbohydrates. And you look over there at Quick Check. Don't forget that. Use that particular component of the textbook. Okay, so let's get into lipids. We got a few more minutes, and we'll see if we can knock it off in about 10 minutes. So lipids, still made of carbon, hydrogen, and oxygen. And again, you flash back. Make sure you do that. Just get in the habit of doing it. It's going to test you, and you want to answer those questions. So carbohydrate, it says lipids like carbohydrates, carbon, hydrogen, and oxygen. And you see it says include fats and oils, still made out of the same three elements. Okay? Keep those terms useful to you, okay? Now notice in the come down 1, 2, 3, 4 lines, whereas glucose, C6, H12O6, has an equal number of carbon and oxygen atoms. It's not going to show up like that in a lipid. Has a number of carbohydroxyl groups, but the lipid has this kind of formula. Cut these advertisements coming out. I don't know if they bug you or not. But anyway, you see you got a lot of carbons, basically twice the number of hydrogens, but you don't have but just a couple of oxygens. So the formula, again, is different. I mean, the formula is different, therefore the substance is different, even though it's made of the same three elements. Now, as you come down to where you see the C15H31 and COOH, you see it says carbon and hydrogen are its main components. Oxygen is very much a lot smaller. The predominance of carbon and hydrogen atoms in the lipid molecule make it overall very non-polar. In other words, they're sharing the electrons equally. Covalent bonds, non-polar covalent bonds. But because they're not polar, because they are non-polar, you see it says they're hydrophobic. They will not dissolve in water. That's why in your Italian dressing, you see the water and you see the oil. Okay, or you might see the vinegar and the oil. Vinegar's got, we say it's an acid, but it's got a big component in there that's water. And water is polar, but the oil is not. That's why they separate. Of course, we shake it up, and pour it all over the salad. You got all those good flavors in there. So, we live with it, and we don't think anything about it. It's just the way it is. So, notice it says lipids will dissolve in and can act as a solvent for other non-polar substances. So you can mix non-polar substances and they will dissolve. But you can't mix a non-polar substance and a polar substance to dissolve in each other. Those charges make the big difference. So now we come down to some examples of lipids, fatty acids and triglycerides. Now you see it says a basic lipid monomer is a molecule called a fatty acid. So you think of fat and you think of an acid. Well, where's this acid coming from? Hang on, we're going to look at it in just a second. A fatty acid consists of a carboxylic acid group. That's the COOH. That's the acid component of this fat, because that is on there. And you've got all these carbons in a line. You got hydrogens filling up those carbons, and then you got a COOH. That's the acid, so we call it a fatty acid. Look up at the top, and you see it says they can have anywhere from 4 to 20 or more carbons. And notice this. Here's what's real important to us. Well, it's all important, but the hydrocarbon chain may have one or more double bonds between its carbon atoms. One or more double bonds. You remember how we talked about single covalent bonds, double covalent bonds, triple covalent bonds. So if they have one or more double bonds between the carbons, that's just another way we can organize them, classify them. So you see, the first thing we come to is saturated fatty acids. Has no double bonds. It's all single covalent bonds between the carbons. And so it's said to be saturated. You can look below and you see the yellow box right below that paragraph, and you don't see any double bonds between carbons. You see single bonds. That's why they got a single line there. So that is a saturated fatty acid. Those are the ones that are not real healthy for us. Now, we all eat some bacon and so forth, but if we don't eat much of it, it's not very harmful. But in some people, it starts clogging up their arteries. So saturated fats can shorten your life. It's better to have the unsaturated, which you get typically from nuts and fish, good old salmon and stuff like that. So you see the saturated fatty acid, come down to the next one, and you see that bend. You see a double bond. So those don't tend to clog our arteries. They're good for us. We need them, as we'll see in a little bit. But that's one double bond, so we call it an unsaturated fatty acid. If you come down to the next one, you see you have two double bonds between those carbons. And so we say it's polyunsaturated. Mono means you just got one double bond between those carbon atoms. And then polyunsaturated means that you have several double bonds. They're good for you. You can look over on the second column. You see in the second column the monounsaturated, the polyunsaturated, and the omega-3s come. That's the mono and polyunsaturated fatty acids that are good for you. They sell them to you by little capsules. It's probably better to eat the fish. It's probably better to eat the nuts. Walnuts are good at it. Peanuts are good at it. So you could research that and find out what are the best nuts. But they tell you it's good to have eat nuts in your life. You put nuts in your salad. Some of you like peanut butter. That's good. It's got unsaturated oils in there. So that's real good for us. And we need those fats. As you see this, we think of fat sometimes as, it's disfiguring and so forth, but it does fill out your face. Keeps you warm. It's got possibilities. It's got things it can do, responsibilities it can carry out. The problem is homeostasis, the right amount. Anything in excess can create a problem in the body, whether it's water or whether it's fatty acids. So you can read about the mono and the polyunsaturated. Now, notice in the last paragraph on the second column, Our bodies cannot package fatty acids into long chains as they can monosaccharides. Fatty acids are stored by linking 3 of them via dehydration synthesis to a modified 3-carbon glycerol. Look below, and you to the left, you see the molecule glycerol. It's a 3-carbon, we might say it's a 3-carbon alcohol. It used to look like that with those OHs on there, but then we have the enzymes to hook the fatty acids to the glycerol. You see the blue hydrogen on the glycerol? You see the blue OH on the fatty acid? The water is taken out, the 2 hydrogens and the oxygen's taken out. An enzyme causes that, and look below and you hook it to the glycerol molecule. You do that for all of those fatty acids. The glycerol can only carry 3 fatty acids, so it's called a triglyceride. A triglyceride, and we store that. Now let's look on page 54. 54, and you look in the first column and you come down to the second paragraph, and it says that triglycerides, not fatty acids by themselves, but in the form of triglycerides, where you have to break it down to use it, you see they're in fat cells where they help to insulate our body. That's one good function. They protect against physical shock. They regulate body temperature. And then they're also a supply of fuel. So you got 4 functions there of those triglycerides. Okay, so what we'll do is we'll pick up, we're almost through with phospholipids, almost through with lipids. We got 2 more categories that we'll mention on Tuesday morning. And we'll do the phospholipids and steroids. We'll get proteins done, and then we'll get the nucleic acids done. And we'll be through with chapter 2. And we will have a test on Thursday of next week on those 2 chapters, what we've covered. Do you have any questions, Shakira? You are the one who has stuck here. Why these other kids are not on, I don't know. Knock out an A. Knock out an A. You are capable of doing that. Do you have any questions? Okay, no questions, I assume. All right, I'm going to end this live stream. See you next week, Lord willing. Good. If you have a question, you do that. Okay, you email me. That's great. All right. Have a good weekend, Shakira.